Hello and welcome to ZTEC's webinar on Large Area Eddy Current Array in lieu of PT and MT. My name is Michael Mussman of ZTEC. I'd like to thank everyone for joining us today. As an on-demand webinar, there is no live question and answer section at the end. Instead, you can easily send us a question at any time. Simply email webinars@ztec.com and we will respond directly to you. Before we begin the webinar, I'd like to give you a quick overview of ZTEC. ZTEC is a global NDT leader. For over 50 years, we've advanced the science and standards in both ultrasonic and eddy current technologies, setting new heights in inspection performance, productivity, and predictability. ZTEC's proven expertise and complete product portfolio serve the inspection needs of our customers worldwide in transportation, power generation, manufacturing, and oil and gas. ZTEC is a subsidiary of Roper Technologies. Now let's get to today's session, which will be presented by Jesse Herron.
Hi, my name is Jesse Herron. I'm the product manager for eddy current systems at ZTEC, and I'm going to be doing a webinar covering large area eddy current array in lieu of PT and MT. And in this webinar, we're going to cover the liquid penetrant testing, or PT, and then magnetic particle testing, MT, and go over eddy current array and some basic eddy current testing as well, and then cover the ASME Code for ECA that was recently released, and then do some side-by-side examples of ECA versus PT and MT. And then there'll be some additional ECA examples that we'll go through, and then some conclusions. So liquid penetrant testing, also called PT, is a process where you draw the liquid into the surface, and you're using capillary action to highlight those indications or defects. And the penetrant is either visible in just sight, or you can use a UV light to fluoresce that penetrant liquid and show those indications. And so because it's using the capillary action, it's just for surface breaking defects or discontinuities. And you can do this in metal or other non-porous materials. And so there's a kind of multi-step process to do this. You would clean or prep the surface, and then you cover that surface with the penetrant. Then you wipe off or remove any of the excess penetrant, and then you use a developer to try to draw that penetrant out so that the discontinuities that were indicated are more visible. So it has a lot of advantages. You can do complex shapes. You can do both conductive and non-conductive materials. You can do large numbers of parts at one time, and it does resolve some small cracks. You can get an estimate of the crack size and use like photographs. And it's pretty easy to perform and tends to be low cost from a material standpoint. But there are a number of disadvantages for PT. So one of the things is if you have a material that has any kind of paint or coating on it, or inspected part that you're looking for, you have to often remove that coating to be able to get down to the indications or cracks you're looking for. And then sometimes that can be really hard to fully remove that. You may be able to get some of the top surfaces of coatings, but there could be under coatings or different processes like anodize that are hard to fully remove. Porous materials typically can't be tested with penetrant. They just would have too many masking of the indications. And then anything that's subsurface, things that are not actually breaking through the surface in terms of like a crack, if it's hiding there below the surface, you're not going to see that. And then because you're working with penetrant, you do have some limitations for temperature in the low and high range. So in certain cold weather or very hot weather, you can't use it. It is potential for fire and explosion with the chemicals, and you're also dealing with chemicals, so you have to be aware of the hazards and things that go along with handling all the chemicals. And then once you're done with the test, you have to clean that area, and then you have to reapply paint or coatings to have that part go back in service if that was required. So it's pretty time-consuming process. And then when you're in the inspection, there can be some problems as well. If you had dirt or debris that wasn't fully cleaned, anything underneath that won't show at all. In some cases, you can have too much penetrant in an area, and that will mask small flaws. And in corners, you can have a bleed out where you are also covering flaws. And then when you go to clean it, if you over clean it, you could essentially wipe away any of the indications that were with the flaws. So you could actually remove your testing penetrant. And if you have penetrant testing, the chemicals can degrade over time, which would give you a weaker response, which would make it harder to resolve smaller indications and something that you would expect to resolve, but you can't because of the chemical degradation. And then there tends to be a limit on the amount of size that you can resolve. So on a linear type of indication, 20 thousandths inch, or if it's a round or volumetric, then 30 thousandths inch. So for magnetic particle testing, here you're taking very fine particles and applying it onto the metal, and you're using electromagnetic current to create a indication around cracks, because the current has to flow around those cracks, and the ferromagnetic particles get drawn to that current. They create little fields, and that's what you're looking at for indications. So you have to do this in a couple different ways. So you apply a circulating magnetizing current to create a flow of current through the part, and then this allows you to resolve things that are indications or cracks that are perpendicular to that current flow, because then the current will flow around those cracks. But if you see on the chart over here, if you have something that's in line with the flow of the current, there's really not going to be much impediment of the current through that crack area, and it's not going to resolve the ferromagnetic material, so you're not going to see any indication of that. So it's sort of blind to that orientation, and as you can see, if something has got an orientation that rotates toward perpendicular, it gets better and better resolving. So to address this, a second magnetization is done where you're creating, essentially, you apply your magnetizing current straight through the part, and now your magnetic field goes in a circular motion, and now you pick up things that were in that axis orientation, and that will resolve, and then the perpendicular ones will not resolve. So that's how you get the full coverage. It does require two setups. This is an example of everything that you would have to do this kind of magnetization and setup for MT. So there's a lot of equipment that goes into it. Some advantages with MT is that you can do complex shapes. You can actually resolve cracks with paint or material in the cracks, so it doesn't totally require removal of paint. You can do a large number of parts at one time, and small cracks can be detected. Subsurface discontinuities can be detected, and you can even go through like a thin non-metallic coatings. So you get a approximate estimate of the depth size, and like PT, this is a fairly easily learned technique and can be low cost in terms of the materials that are used. Again, though, disadvantages with MT is that you're only able to do ferromagnetic materials, ones that can be magnetized. You do have to apply a very high current to your part, and afterward you need to go through a demagnetization process so that you don't put a part in service that's magnetized. You have to take really high care to make sure you don't put any burn spots because of the current. And in some cases, you do have to remove the paint and coatings to be able to get this to show the indications. Detecting small defects below the surface can be challenging. So you can get small defects on the surface pretty well, but when they're subsurface, that can be hard. Afterward, you have to clean all of the magnetizing particles, the ferromagnetic particles. And then, as we talked about, there's multiple orientations that are needed to be done. So it takes multiple setups to do the test. And so all of that can be time consuming and does require some skill to be able to do it properly. And then in the end, you have limited ability to record the inspection other than like a photographic evidence of the magnetic particle. When you're in the middle of the inspection, you have the common problems of having to remove excess particles, which can cause you to miss small flaws. And then if you have too many particles in an area, it also mask smaller flaws. If you don't apply enough current amperage, then the smaller flaws won't create big enough fields to see them against kind of the background noise. But then if you apply too high of a current, you're going to start getting false indications that often occur along part edges and things like that. So that would not be good to do that. So you're having to find this kind of medium point of current. And as you are dealing with these orientations of magnetizations, you can get them to occur in the wrong direction. So you may not be seeing something because of that. And then the ferromagnetic particles themselves can be contaminated. And if you have that happen, it may not respond like you would expect with a ferromagnetic particle, and it may get a poor response. So for eddy current array, starting off just going through real quickly on just standard eddy current, it's essentially a wound coil, or sometimes it can be a printed coil on a circuit board. And these coils, you put an alternating current through it, and it creates a field within your part. And then that field will flow around any type of indications or flaws that are in there. And then the coil detects those magnetic field changes, and you get a response. And so you can go through non-conductive coatings, and you can test both ferrous and non-ferrous materials. You do need to have conductive material to be able to create the eddy current field. So some benefits: you don't have to deal with surface preparation or chemicals. With the instrument, you do get a computerized record of the inspection. And then there's a little bit of dependence on the user training, because you have potentially, if you're not engaging the coil correctly into the part, you can have some false indications in that. So you need to make sure that the user's trained properly. And then the speed for a single coil can be slow to do a coverage, because you're essentially having to paint in or raster scan an area. And at the bottom there's a example of a single coil eddy current probe. So eddy current array takes those single coils and now puts them into a grid of multiple coils, and you can now take the signals between coils in both the direction that you're scanning, which is axial, or transverse, which is perpendicular to the direction that you're scanning. And so if you had an array probe here, you would scan it in this direction, and this would be your axial direction, and this would be your transverse direction. And in here you have a number of coils that are firing in a coordinated way to create essentially a full view of this area as you scan along. So you're not having to do trying to use a single coil to try to cover an area. You use this array of coils to get the coverage across that one area. And because the multiplexing of the signal across these coils is very fast, you're able to get fairly high scan speeds and know that you got full coverage across that area. And what this ends up doing is creates essentially like a 3D image of that area and what's going on both on the surface and in the material subsurface. And you end up with a fairly high confidence that you've gotten full coverage across this area, and it gives you a high probability detection. And that goes along with the repeatability of being able to do this with inspectors. So taking that human element of someone trying to scan with a small coil, you get a lot of variability in the results. Here, there's a lot less variability. And then with eddy current, you can operate in a fairly high range of temperatures and environmental conditions. So this is visually what's going on within the array. You have a transmit coil and 2 receive coils in that axial direction, which is the scan direction. And again, this is the scan direction. And then you have, if you have some type of indication in that direction, it'll be picked up by those signals. Then if you have an indication in the other orientation, you have a transmit and receive in the transverse direction. And that will be picking up those orientation indications. And then this set of 3 transmit and receives occurs across the entire array. And this is happening at a very fast rate as you instruments controlling that. And this is how you get that full coverage. And so this is very quickly scanning across. And as you progress forward in your inspection, you get the coverage. So you can have different channels. You can have an axial sensitive channel and a transverse sensitive channel. And so your result down here, this would be the scan direction. So that would be axial, and this is transverse. And so if you have an axial sensitive channel, it will pick up anything that's oriented in that axial direction. And then the opposite is true for transverse. It'll pick up the transverse, not the axial. You can then also merge these two into what would be called like a merge channel, where you're seeing everything that the array is picking up. So both axial and transverse indications together. So it's marrying these two things together to see a single channel. And what this allows you to do is to start the characterization process of what things are oriented in what direction. So if you see something in an axial channel and not the transverse, then you know that it's crack-like and it's in the axial direction. Then the opposite, if you see something in the transverse channel and you're not seeing it in the axial, then it's crack-like in the transverse direction. If you see it in both channels, so if you're seeing it in the axial and the transverse, what you're likely looking at is something that's volumetric, meaning it's got a circle or a volume to it, maybe like a pit or corrosion, and you're seeing both axial and transverse at the same time. And so that's how you can characterize between crack-like or volumetric-like using eddy current array. And that can be very powerful to convey to asset owners or whoever owns the part that you're inspecting, what type of indications they're getting. So this is a video showing the actual scanning, and this is a subsurface scan. And essentially, in one pass, you're just painting that surface and picking up anything that's below it. And here you can see there was a scribed ZTEC in that plate, and you can quickly see exactly what was in there. So you get a a picture of these flaws. And it's very easy to tell what's an indication and what's not. And that leads to that high probability detection. So this process has been done enough now that it's made it into the ASME Code. And this is for boiler and pressure vessel. In Section 5, Article 8, there's two appendixes, Appendix 9 and 10. And the 9 is for ferromagnetic and non-ferromagnetic materials. And then 10 is for welds. And this is for eddy current array examinations. So these go through essentially all of the things that you need to do that inspection. It goes through your general requirements, what equipment you need, the settings for the technique setting, the application requirements, how you go about calibrating it, doing the acquisition, and then the analysis after that, and the reporting. So if you are interested in developing eddy current array procedures, you can reference this ASME code, and it's got all of that detail there. All right, so looking at ECA in lieu of PT, and this is now side-by-side examples where you have a inspection done in PT and you can see it in eddy current array. So there's kind of two ways to apply eddy current array when you're doing these replacements or wanting to do something other than PT or MT, is that you can do a full replacement of the entire inspection. And so here you get very reduced inspection time. It's does not require all the surface preparation, and you can get a digital record of that inspection, and you can use that for historical comparison if you want later on. And you have that very high probability detection using the C-scan imaging. So there's a lot of benefits to doing full replacement. Sometimes it can be hard to get to that level of complete replacement. There's a lot of historical data associated with doing the PT and MT, and another approach would be to actually augment the PT and MT. So you would use the eddy current array to do large area screening for indications. And then when you find something that's of interest, that you think there's something there, then you can focus and do a very small area with the PT and the MT. And that would have a significant cost savings because you're not having to do an entire area doing all the surface preparation, the chemicals you have to deal with, the cleanup, and if you have to reapply paint or non-conductive coatings afterward. So you can do this as a way to supplement, essentially. So in PT, there's what's called a Tam Panel, and this is how they essentially qualify the penetrant that they're going to use. And over here, you'll see 5 different crack sizes or crack patterns. So there's a large down to a small. And then they're using this to see if the penetrant has degraded over time, if you're having problems resolving sizes you were able to resolve before, or if just the penetrant itself has limitations. So this is what it would look like using PT. And you can see very clearly the larger crack pattern. But the smaller ones are fairly hard to make out. Often these smaller ones are not really qualified with the penetrant. There are different types of penetrants, ones that are better at resolving these smaller patterns. And so you sometimes have to do multiple penetrant exams to get full coverage. But this is what it looks like with eddy current array. So the largest crack pattern, it's very, very clear. But the smallest crack pattern, even that one shows up extremely well against the background field. So this would be your just general noise plane, your base material, but you can clearly see there's the smallest crack pattern there. And when you talk about POD, anyone who looks at that would think that there's some kind of thing of interest going on there. And that can be confirmed that there's some type of indication or crack. Also, if you look at that plate, it took less than a minute to set up and perform this exam. And the actual inspection, once you're set up, takes just seconds. You can scan it, and in seconds you have this data. And then you can save this data file if you want to have historical record or see if things change over time. And then for visualization for ECA, it doesn't have to be in this sort of kind of rainbow color of green to red. You can also have a number of color schemes you can apply and even make it look like a penetrant test if you are using a red dye penetrant, or if you're using a fluorescent, you can do it in greens. So you have the full ability to customize these color palettes, and even in shading of dark to light here. And then you set thresholds. So you have multiple threshold points, and you're essentially setting voltages of the eddy current signal if you want it to have a color change at a particular point, and then gradient from there. You can customize all of that. And the end result is you get a C-scan eddy current array inspection that looks like your penetrant test, and you can use this to compare side by side the penetrant and eddy current array. So for some examples, this is an aircraft stringer, and this was done with dye penetrant. It's a fluorescent dye, and this particular part is aluminum alloy. It was wrought worked, and it has a stress crack here. You can see the stress crack showing up around that whole part, and it was about 1 1/4 inch long. So that same part scanned with eddy current array, the stress crack is right there, and you can see clearly the indication occurring. You can also see that there's more going on with the crack than just a single continuous crack. There's variations in the size and depth, and you get that information when you use eddy current array. You can go in and do analysis on what's really going on in there, and sometimes that's important for how you're going to respond to that indication in that part. If you find something that's really deep in one spot, you may need to focus in that area and do the repair. Maybe not the entire spot has to be repaired. That is the stress crack shown. This is eddy current array with a color scheme that looks like the fluorescent. This is another aircraft stringer, also done with dye penetrant. Here there's a really long 2.8 inch long crack along the fastener holes there, or above the fastener holes. And again, here with eddy current array, this long crack, it's not just one long continuous crack. It was that these cracks were occurring with each hole. So there was some stress that was occurring at each hole point, and it was creating cracks that were forming. And over time, if you were to monitor this, these cracks would probably eventually join together. But here you can see it on the color scheme with the C-scan, clearly showing the 4 cracks here. This is an engine blade done with dye penetrant. This is actually a titanium material cast in weld. And here there's a tip crack. You can see the tip crack right there. But there's also some cluster porosity going on the pressure side of the engine blade. The tip crack was about 0.3 inches long, and the pressure side, the cluster porosity, was about 1 1/4 inch diameter. So this is the porosity. You can see this occurring with all of this indications here, and you can also see it there. And then the tip crack, you can see this really clearly on the eddy current array. That's the tip crack. I mean, there's no way you can not see that. And very clearly resolves against the background there. And that's the crack right there. This is a forging part, and It's Inconel 718, rot worked as well. And in this case, there's a forging lap issue and a forging burst. And this is the forging lap. You can see down here in the lower part of this part area. You can see the scan here that the signals over here is the edges. So that happens when you scan across an area, you hit an edge, you'll get liftoff with the eddy current array. So it is worth knowing where you have liftoff and where you don't. But when you have known contact with that part, you're clearly seeing indications of this forging lap. And then the forging burst on the inside corner here is also showing up. And you can see, again, multiple things going on within that burst area, different depths and sizes. So moving to MT, this is looking at side-by-side examples of eddy current array and MT. Here you have carbon steel, and this is something you can do eddy current array on. Typically, you're getting surface breaking cracks or indications with eddy current array for carbon steel. Here you have just a base metal crack. It's 0.6 inches long, and then you have a root crack that's occurring in the root area of that weld, and that's 0.3 inches long. And so here you can see with the magnetic particle testing, it looks like two different cracks. But you look at it with eddy current array, and the base metal crack is actually two cracks that have almost joined together or just barely joined together. And so you don't really get that level of detail with the MT, but you do get it on the eddy current array. And then the root crack, you would be hard to tell, that there's two different things going on here, but the root crack is a continuous, just one crack point. And now you know that with the eddy current array data. Same thing with the other view. You can kind of see here also, you can take your cursor point in eddy current array and have a impedance view, or some people call this a lizard view, and you can get voltage and phase information on any particular point in the array. And that's important for people who know how to do sizing, depth sizing, using depth sizing curves. If you have that level of information, you can do additional analysis on the indications. And so what you can do is, go to a particular point where there's a peak or the worst case area, look at the voltage and phase in that area. You can also get measurements. You can see there's some measurements going on here. You get axial length, which is in this direction, transverse length in this direction. And you can start your kind of surface sizing of that crack area. You can use your cursor as a reference to give other types of measurements and things like that. So if you have like some known location on the part, you can get a cursor reference. Moving to an engine ring. This is stainless steel. It was a forged and rolled part. And here there's a machine tear. You really, you're looking at this stainless steel part, you wouldn't know that there's some kind of mark or indication going on here, but you put it under MT and there's clearly some type of crack or thing going on there. That's a machine tear, and it's 0.2 inches long and very easy to resolve with the eddy current array. So again, visually, if you looked at that part, you would not think that there's something going on. To get the answer with MT, you have to go through the whole process of adding the chemicals, going through the magnetization process and fluorescing it, getting a visual look at everything, and then you finally get your answer. Eddy current array, you have your setup, scan it in a few seconds, and you're getting this result right away. So it's very, very powerful to be able to do that. A lot of time and cost savings. Here is a mild steel aircraft latch, and it's a forged and rolled part, done with wet fluorescent particles. Here you can see there's some forge laps going on, and they're about 1.5 to 2.5 inches long. And here, very easily able to see these two forge laps here with eddy current array. One thing to note as we're going through these examples is that there's a wide variety of processing on these parts. You have machined and cast, forged, wrought. The eddy current array is able to handle all these different variations. So it's a very versatile technique. So here's some additional examples. In this one, it's going through doing a train wheel inspection. So you can see there's a train wheel. This is the contour of that train wheel. And the goal here was to try to inspect this in 3 passes or less. And so you have all this geometry that you need to deal with. And to solve this, there were some custom forms applied to the printed circuit tape probes. And these forms are specifically molded to match the contours in these 3 geometry areas. And then with these 3 passes, you're able to get the full coverage of this entire train wheel. And again, you can do a customized color palette if you want it to look like your dye penetrant testing. This one is the red dye penetrant testing visualization. And you can set your thresholds for certain voltages that you want to find there. These probes have a UHWM wear surface to help improve in the longevity of the probes. This is an aircraft wing spar, and this one was just done with a visual inspection. And there was some transverse cracking going on here. So you can see in this area here, this one was actually corrosion in this area. And you know it's corrosion because when you look at the axial channel and the transverse channel, you're seeing essentially the same thing. So there's no disappearance of the signal in either one. And so you know there that you have some level of volumetric going on. In the other area that was found visually, there's looking at the axial and transverse channel, you can start to see that there's differences between these 2 channels. And knowing that there's commonality here in this and these signals, that's the corrosion. And so you can see it in axial and transverse. But in the lower area, you're seeing something in the transverse channel you're not seeing in the axial channel. And so that's indicating that there's transverse cracks in these areas. And again, being able to characterize that level of detail is very powerful to be able to convey that information. This is another example of stress corrosion cracking in carbon steel. And this is a very problematic type of defect that can occur. In this case, there's heavy axial cracking happening with many sizes along this plate. And using the eddy current array, you can see all these axial cracking that's occurring. And highlighted here with an overlay of the palette C-scan, you can see exactly where those cracking indications are occurring. So you're giving that exact information, able to do size and scale of the cracking. But with stress corrosion cracking, sometimes it's not just cracking. You can have multimodal damage where you're getting heavy corrosion and cracking occurring at the same time and in many different sizes. So you can see here, there's a lot going on, but it's not quite clear exactly what's going on. So you take that part and you scan it with eddy current array, and you can see a large number of indications all over the place. It's only when you look at the differences between your axial and transverse channel where you can start to really discern what's going on in these different areas. So here you can identify there's axial cracking going on here. This is axial direction, and you're not seeing it in the transverse. In the lower corner here, you're seeing this area of indications, and you also see it in the transverse channel. So you know there that that's an area of corrosion. And so being able to take a lot of information, there's a lot of stuff going on in this part, and then start dissecting what is going on, and then relay that information. So in conclusion, the dye penetrant and magnetic particle have a number of disadvantages that do make them suitable candidates for full replacement with eddy current array. You can find a lot of small and large indications with ECA in just one scan, and you don't have to do a bunch of separate exams to get that information. And it's not going to be sensitive to these kind of, if you have low and high sensitivity penetrant materials that you would have to deal with, you don't have to deal with that. You can do it through painted or coated surface coatings. You don't have to remove that to do ECA. And then the eddy current array can operate in a wide range of temperature and environmental conditions. So if you're out in the field, you need to do it in very cold temperatures or in a very hot temperature area, you can do that. The axial and transverse channels can be used to characterize indications, and you can characterize those between cracks and volume type flaws. And then lastly, this is not just a fully replace with eddy current array. You can also do an augmented inspection where you do the eddy current array as a large area scan to try to focus in on those areas of indications. And then once you have those special interest areas, you can go in with the PT and MT and do the validation that you're familiar with or have historical record on, or maybe even procedures around doing that. But you can still keep those procedures valid. You just don't have to do as much of it because you've done your initial scanning with the eddy current array to confirm that there's not stuff going on in other areas. So that can end up with also significant savings in time and cost. These are just some references for putting together this webinar. And I want to give a special thanks to Tony Bailey, who helped provide the samples and results for the PT and MT. And it was a lot of help to be able to get those. So thank you for that. And that is the conclusion of the webinar. So thank you.
On behalf of everyone at ZTEC, thank you again for attending this webinar. If you are interested in learning more about our solution or have additional questions, please email us at webinars@ztec.com. To learn more about ZTEC, visit our website or follow us on social media. This concludes our webinar. Thank you and have a great day.